Okay, welcome to the next class on multiple view geometry. Today we'll talk about the last part on actually reconstruction from multiple views. At least the last class on these linear algebra strategies to separate structure and motion. And what we talked about last time was a rather technical class on multiple view matrices and how to encode information from multiple views, so not 2 but 3, 4 or 5 views of points and lines, how to encode that information in matrices and more specifically in rank constraints of matrices. So although rank constraints are somewhat unusual in standard science and it's not actually found so frequently when you study math and linear algebra, you hear about rank of matrices, but at least when I heard about it in my linear algebra class, I was pretty certain that had no practical use. It turns out you can actually make use of the notion of rank in a practical setting, and the rank really tells you something about linear dependency of rows and columns. And what we exploit extensively is that this notion of rank and linear dependency. For example, we constructed this matrix MP, the multiview matrix for points, and you remember it's a matrix that has 2 columns, and as a consequence the rank is at most 2. And in fact, if the rank is 2, then we don't have a consistent pre-image for the point, meaning there is no 3D point that would match all these observations. And so there is no correspondence, and there is an empty pre-image, you would say. And then you have the constraint that you are mostly aiming for in the reconstruction scenario, namely that the rank is exactly 1, meaning these 2 columns are linearly dependent, and that really for 2 columns just says one column is a multiple of the other. And that in that case we have a unique pre-image, so there is a consistent reconstruction. And then we have the third case, of course, that the rank can be 0. That, as I said, really only happens often on the slides. You see rank equals 0. What it really means is that the matrix is 0. A matrix that is non-zero doesn't have 0 rank. So the only 0 rank matrix that you can have is a matrix that is made up of all zeros. And in that case, we have a pre-image, but it's not unique. So there are multiple possibilities. Of course, you can ask yourself, does that really happen in practice? Is there scenarios where I have multiple observations of a point and still there is not a unique pre-image? Of course there is. What can happen is, and in fact that often happens in a car driving scenario, when you do image-based reconstruction from a driving car. We've worked on this problem for a number of years. One of the major issues is you're typically driving in a straight line. And in addition, if your camera is front-facing, you're mostly interested in what happens in what's called the focus of expansion in the driving corridor. You don't care so much about reconstructions of the trees on the left and on the right. What you care about is what happens in front. And unfortunately, if you're actually driving towards the structure, then you see the same point multiple times, but it's very hard to determine its 3D location. Because you cannot estimate its distance. If, for example, if you're moving exactly towards that point, you will see the same point over and over. You have multiple observations, but they're redundant in some sense. And so this is a scenario where you have multiple images of a point and still you're not going to compute a meaningful, unique pre-image. You will have an entire line of possible points. Today I wanted to then talk about how to use the multi-view approaches to do structure and motion reconstruction. And the idea, you remember, we try to follow here along the lines of the 2-view case. That is to say, we are trying to reproduce, in some sense, the 8-point algorithm. And the idea of the 8-point algorithm was that we decouple a problem in a way that we first have the epipolar constraint that can be put together with multiple points that we observe, 8 points or more, into the 8-point algorithm. And then we see we have an algorithm where we can estimate the camera motion without actually knowing the 3D location. And once we have the camera motion, we can then estimate the 3D location. And both of these solutions can be solved by linear algebra methods. And so what we'll do here is we'll see how far can we get with linear algebra methods. And we see that we have closed form solutions, but in a second you will also see that unfortunately these solutions are not of the same type as the 8-point, in the sense that the full decoupling of motion and structure estimation is not feasible here. So this is what we pursue. Here is again the multi-view rank constraints. The rank being less or equal to 1 basically says that one column must be a multiple of the other column, i.e. there is some linear combination with some factor that I call alpha j, such that this is 0. And we now consider, as I said, not just one point observed in m images, but n little n points indexed by the index j. So xj1 is the jth point observed in image 1. So we have all these observations, and then we have the multi-view rank constraint for each of these points, and for each j we have such a constraint saying this column plus some factor times that column must be 0. So there exists an alpha j such that this linear combination is 0. That's just saying the rank is less than 1. Less or equal to 1. And in fact, you can show that this parameter alpha j that you have here that models this linear dependency is nothing but 1 over lambda 1j. So that is exactly the depth of the point j with respect to the first camera. And so we have this equation. It contains the 3D parameters. In here, the alpha j is 1 over the depth. It contains the 2D coordinates and the camera motion. Now, what you can see is, if you look at this constraint, it's a linear equation system, and all of these terms are linear in the camera parameters. That's a good thing. In some sense, it's almost constructed in this way to have a linear dependency. So there's the rotation matrix, translation matrix modeling the inter-camera transformations. And these we want to get at. How do we do that? Well, you see that these expressions are linear in R and in T. So there is a way to basically write them like that. To write this whole left-hand side that you have here as some large matrix times Ri, S, and Ti. And here what we did is it's linear in R, but R is a 3x3 matrix, of course. It's a rotation matrix, but it doesn't matter. What you can do is you can just stack that matrix into a long vector. The expression is linear in all the coefficients of R, so we can just put all the coefficients of that matrix R in one long vector. So what we did here is we just rewrote, in fact, this is what this matrix Pi looks like. It's a 3n by 12 matrix. So what we did really here from the last slide to this one is just rearrange the terms such that we have the unknowns in one long vector. Why do we do that? Of course, so we can apply the linear algebra machinery. Whatever the unknowns are, you stack them in one vector, and then you have some linear transformation of this vector that equals 0. And so we can say, very good, that means the unknown camera parameters are in the null space of this matrix. They are a vector, and in general a non-zero vector. Of course, the 0 vector, as we know, is always mapped to 0. This is the scale invariance of the reconstruction. So that pursues us, like it haunts us through the entire class. The fact that image-based reconstruction can only be estimated up to scaling. So 0 is always a feasible solution, and as you know, typically we resolve that issue by normalizing, somehow saying the baseline should be 1. Interestingly, in the multi-view scenario, that means you only need to specify one of the baselines, of course. So if the camera keeps moving around and you see the same structure multiple times from one camera, from another camera, from the third, this non-uniqueness of the reconstruction, this scale invariance, basically means you have to fix one of the baselines. And then, of course, the other ones follow along. So this is a 3n by 12 matrix, and the solution we are looking for is in the null space. And again, the same reasoning, we want a unique reconstruction. Therefore, we want to make sure that this matrix has rank 11. It has at most rank 12. If it has rank 12, meaning it's full rank, then only 0 is mapped to 0. So remember, what we exploit is the fact that for matrices, the dimension of the null space and the rank are related. If a matrix has full rank, then the null space is the 0 vector only. So to have a non-zero vector in the null space means the matrix cannot have full rank. It must be rank deficient. But we want the null space to be exactly one-dimensional. We don't want a two-dimensional. So we want a unique solution up to scaling. That means a one-dimensional null space. And that means the rank must be 1 less than the full rank. So we want the matrix to have rank 11. And now you see there it's a 3n by 12 matrix. It turns out that if you have 6 or more points, if you have actually more than 6 points, then you have rank 11. For 6 or less points, the matrix is rank deficient. It's not quite obvious, this fact, that because with 3n, the number of rows of this matrix is actually, so 3n is actually, for n equals 5, we already have 15, but it turns out that these three, each of these three, they're not all linearly independent. And that is the reason that only for n larger than 6 do you get rank 11. So it's much like in the 8-point algorithm. There we said that we need 8 points to have that one-dimensional null space. Here we get away with 6 points. So that's actually better. In some sense, we need fewer points in these M images. And then we can compute the solution very much like in the 8-point algorithm. We take the matrix, we compute the singular value decomposition, and we say that the solution is the vector associated with the smallest singular value. But there is one aspect that, so we are saying here that we follow very much along the lines of the 8-point algorithm and of the 2-view setting. So use singular value decomposition to compute the solution for the camera transformation. But there's one thing you should keep in mind, and that is we have the parameters alpha 1 to alpha n in this matrix. And these parameters, we go back one slide, are the depth values. So this solution doesn't fully decouple structure and motion. Once we estimate motion, here's the motion, we need to have the structure. So in some sense, this is not exactly what the 8-point algorithm did. The 8-point perfectly decoupled things in a way that you could estimate the motion of the camera using singular value decomposition without having the 3D parameters. Here, they're in the matrix. So that's not exactly a full decoupling. And so, but nevertheless, what you can do is, let's say you have some estimate of the 3D structure, these alpha parameters, then you can estimate the camera motion. And in turn, once you have the camera motion, you can solve for these parameters alpha j. The way you do that, I said here a least square solution. What you do more specifically is you have that linear combination. It should be 0. So what you do is you take the norm squared and minimize it with respect to alpha. And alpha is just is a scalar parameter, and so it's actually a quadratic term in alpha. If I solve it, I get a linear equation system. Right? So the equation is going to have the form something like a plus b alpha squared, and then if you minimize this over alpha, then you get essentially, you can solve this, you can square this out, and you get a linear equation system, and then you have to divide by the constant term, and this is this one. So more specifically, the structure is that you have a sum here, and ai, bi are these coefficients that you have here. Sorry, this one and that one. So this is a linear expression, and if I take the square and sum over all points, then I can, over all images, sorry, I equals 1, 2 to m, then I can solve this. And so this is called, I think we may be doing that in the exercises, that you derive that solution, but it's just, you say, find the alpha that gets it as close to 0 as possible in the least squares setting. And so this way we have a solution for alpha, and remember alpha was 1 over the depths, so here's our 3D point. This is the depths, lambda, and lambda is the same as 1 over alpha. And so these so lambda j is 1 over alpha j is for the point xj here. And so we can estimate the 3D location of the point with respect to the first image, so that's that inverse depth, if you will, and we can estimate the camera motion, but what we see is that the solutions are not decoupled, in the sense that the estimation of the camera parameters requires the knowledge of alpha, and the estimation of alpha requires the knowledge of the camera motion. But, it is in that sense an alternation that you have to pursue to get the solution, but what is nice at least is that each step of this alternation is a closed form solution, right? Because I can compute this expression in closed form, and that is the optimal alpha for the given camera, and vice versa, we can compute the optimal camera for the given alphas. So I said down here, as for the two-view case, these spectral approaches do not guarantee optimality in the presence of noise and uncertainty. We're not minimizing the reprojection error, right? So it's not the bundle adjustment where you actually say find a consistent reconstruction such that the projection of my 3D points into the images is as close as possible to the observed points. That would be the bundle adjustment here. We don't minimize that reprojection error, but we do these least squares approaches for these linear systems, and that gets us, and then so these linear systems, we can solve them in closed form. And so it's not optimal, but in addition, beyond this, in contrast to the two-view case, it's not fully decoupled. Once we estimate the camera motion, we have to know the structure. And so the question is, how do you do that? One strategy is you initialize using the 8-point algorithm. So you have m images, you take, say, the first 2 images, run the 8-point, it gives you some reconstruction, some depth values for that point, and then you include the following images and do this multi-view approach. Once you have estimates of alpha, you plug them in here, you do SVD to compute the camera motions. Once you have the camera motions, you compute alpha and you iterate. And I'm saying here you can do this in a batch mode or recursively, that really depends. You can either use all cameras that you have to estimate alpha, or you can just use the ones that you've already computed and then do that recursively. So that you can do, but you see there are two drawbacks here. One is that it's not statistically optimal. Once you have noisy data, the question is how well does it perform? And secondly, it is an alternating approach. The 8-point was not alternating. The 8-point is a solution for the camera that doesn't depend on structure, and once you have the camera parameters, you can estimate the structure. So it is slightly more involved, and with these two drawbacks in mind, there is a question of how practically useful this technique is. But it is at least interesting to see that the multi-view scenario does give us additional information that we can exploit here. Another case that I've already talked about is the aspect of observing not points but lines, and for the points we constructed a multiview matrix which we called MP for points. What I will do now is the same for lines. You can also construct a multiview matrix, and there we will see that for the observation of lines in multiple views we actually have a whole lot of constraints, more than in the case of points. And here is how this works. So we saw already for the lines we had constructed this matrix, an m×4 matrix, and we said that this matrix is such that the rank is at most 2. The reason was that for the points of the line, remember the points of the line we represented as large x in 3D is the base point x0 plus some offset vector v scaled by some parameter mu in R. And so that is the line we observe here in 3D that has some base point x0 and some offset vector v. And so going through different mu's, we can get all the points of the line. And we know that once we apply WL to the points of the line, projection into the image should be orthogonal to the vector Li that defines this pre-image. And so we know in particular for x0, WL x0 must be 0, but also WL times V must be 0, because it has to be 0 for all points of the line. So not just for the base point, but in addition also for V. So we have this expression. We know these two vectors are in the null space of WL, and so we know instead of having rank 4, it can have at most rank 2. Otherwise, we don't have that two-dimensional null space. So this matrix is a m×4 matrix with rank less or equal to 2. What we now do is very much the same trick as in the case of points. We multiply that matrix. We first put ourselves into the camera frame of the first camera. That is to say, the projection matrix pi1 is nothing but the identity and 0, which means that WL looks like this. So here we have L1 transpose 0, and here we have the other camera transformations. And once we are in this representation, so in the coordinate frame of the first camera, we have a 0 here, and now we know this matrix WL is at most rank 2, and what we do is we multiply it with an appropriate matrix such that these two entries become 0. And this matrix in particular is a matrix that is full rank, because this is rank 2, this is rank 1, and this is another rank, so it has rank 4, and since it's a 4×5 matrix, that means it's a full rank matrix. And that in particular means that the rank of this product is still the same as the rank of WL itself, because multiplying a matrix WL with another one that is full rank does not affect the rank. Meaning this product is also rank less or equal to 2. And this is interesting because we have zeros here. And so we know this column here contributes 1 linearly independent vector, and the rest of this can only contribute 1 more linearly independent vector, meaning the rest has to be rank 1. So whatever follows, this submatrix here is at most rank 1. And so this submatrix we call the multiview matrix for lines. Here it is. That is a submatrix, and in fact that submatrix is an m-1/5 matrix. And now we said that it has to be rank at most 1. Meaning the rank of this product is less or equal to if and only if that submatrix has rank less or equal to 1. Otherwise you cannot get, otherwise you would have, see, the rank of the whole matrix is the rank of this one plus 1, because here we definitely have a linearly independent vector. And so we have that submatrix, we call it the multiview matrix for lines, and that has rank less or equal to 1, and that is not a very trivial constraint, because for sufficiently many points, let's say I have 6 or more points, 6 or more images, of the line, so m is 6, then this could in principle have rank 5. Right, it's an m-1/5 matrix, and so saying it has at most rank 1 is a very strong constraint. But here again we see that for lines the number of images is important. If we have 2 images of a line, this matrix is a 1/5 matrix, and saying it has rank 1 is not very helpful. Right, and so here we see for lines we always need m must be at least 3 or more. And once we have higher m's, the rank constraint becomes stronger in some sense. And so the constraint here says that the meaningful pre-image of m observed lines can only exist if the rank is less or equal to 1. And then we have, as you can imagine, multiple cases depending on whether we have a pre-image or not. If the rank is 0, then we have a pre-image, but it's not unique. If the rank is 1, we have a unique pre-image. If it's higher than 1, then there is no consistent reconstruction, no pre-image. Now, as in the multi-view setting for the points, we can study that constraint and see what specific relations pop out of it. So this is often the case when you have rank constraints. Often these constraints cannot be directly used to compute things, right? Just like you saw in the structure and motion problem, we cannot directly compute structure and motion from the rank constraint, but what we use is we interpret that rank constraint saying, say if we have here these two, the saying that certain columns or rows must be linearly dependent. And so this is what we do here. We look at what constraints does that imply, that rank constraint on the multiview matrix. And the constraint that it implies is, one of the constraints it implies, we can see that the row vectors must be linearly dependent. So meaning we have a matrix here with m-1 rows. The statement that it has rank 1 means all the rows must be linearly dependent. More specifically, there's only one linearly independent row in this whole structure. And that means that each row must be a multiple of the other, meaning this, in particular, this expression L2 transpose R2 L1 hat must be a multiple of LM transpose RM L1 hat. And that we can write like this one. So Li transpose Ri L1 hat must be proportional to Lj transpose Rj L1 hat. And this, so one must be a multiple of the other one, and this can be rewritten in this constraint. And I'll show you it's a similar reasoning that we have had before. What you have here is this expression is a multiple of that expression. More specifically, it means that the three vectors, Ri transpose Li, that is the transpose of this vector, and then this here is nothing but the cross product of L1 and the vector Ri transpose L. So the cross product of this one and the cross product of these two must be proportional. So basically the vector L1 that we have here and here, and the vectors Ri transpose Li and Rj transpose Lj, these three vectors, they are coplanar. Because if I take two of them, the normals of the plane they span are proportional, so they have the same normal. And that means they all must live in the same plane. So these three vectors are coplanar. And then you can do the triple product of these three vectors, and it must be zero, meaning the volume spanned by the three must be zero, and that is this expression here. So that is nothing but the triple product. It's the cross product of L1 with one vector and then scalar multiplied with the other vector. And so that is the triple product of these three vectors. And they are coplanar if and only if their triple product is zero. And so this is often a bit confusing, saying this expression is a multiple of that expression. Why that is equivalent to this constraint, it takes a little bit of reasoning. It's not directly obvious. So when I first read that, I thought, well, how is that possible? But so you can actually derive it in this fashion. Look at this expression, say this is a cross product of two vectors that defines the normal span for the plane spanned by these two vectors. This is the other two vectors, L1 and this vector. And the fact that these normals are proportional to each other means that two vectors span the same plane, means all three live in the same plane. And that in turn can be written as the triple product being zero. What's interesting about this constraint that we get from the multiview matrix of lines is, in fact, that it only involves the rotations of the cameras. Ri is the rotation to the I's camera, Rj is the rotation to the J's camera. There's no translation in there. So we actually have constraints on the rotation of the matrix directly once we observe lines. In addition, there are more constraints, also constraints on the translation. We said here's the multiview matrix. These, the columns here must be the same, must be proportional. And we can use that fact can be rewritten in this constraint. And this constraint, actually, it follows from the general lemma on page 25. If you go back to page 25, here was if you have a matrix where the columns are linearly dependent and they are A1 to AN, B1 to BN, that is equivalent to saying that these AI and BJ, they fulfill this constraint. And so we've used exactly that same thing. If you plug in AI and BI for these columns here, then you get this expression. And so this constraint is, as the previous one, a so-called trilinear constraint because it couples, it depends on three parameters. Here you see Lj, Li, and L1. So and that's why it's called a trilinear constraint. And in fact, what you can show, I don't show it here, is that the two trilinear constraints, this one and this one, they are actually equivalent to this multiview rank constraint. So they contain all the information that you need. And in fact, they're equivalent to this rank constraint if Li transpose Ti is non-zero. That was always kind of the assumption here. What that really means is Li is the vector defining the pre-image. So you observe a line, you have this normal vector on the pre-image, that's Li. If it means there has to be some translation in the direction of that vector. If you don't have such a translation, that means you only translate your camera in basically in that pre-image plane, then you're not going to get additional information about where that line is in space, right? So this constraint that Li transpose Ti, meaning the component of the camera translation in direction of the of the normal on the pre-image, that component, maybe I should get an image. Here's an image, so here's L3. Let's say you observe just one line here in one image, say in the first image, and then you have a camera motion that moves the camera inside that plane P1, then you're going to see the same line over and over, but it's going to always be the same pre-image. So you're not going to get an additional plane P2 that you can intersect with P1. And so you don't get additional information. And this is why that constraint Li transpose Ti non-zero is important to get meaningful reconstructions of lines. And so one calls this case, if this is 0, this is called a degenerate case. And degenerate cases are usually not good, much like in the 8-point algorithm you have degenerate cases. For example, if all points live on a plane in 3D. So there are various kinds of degeneracies, and the issue is that in real-world scenarios they typically don't arise. There are some nasty degenerate cases that do arise if your camera moves on a line or on a plane, etc. But for a general camera motion, you don't run into these issues. But it's important to know in reconstructions that there exist degeneracies and to avoid them if possible. Another way to interpret the rank constraint, and this is again a fact from linear algebra which I'm not going to prove, you can show that for a matrix ML, like this multiview matrix for lines, the rank is about, at most 1 if and only if the so-called 2x2 minors have non-zero determinant. 2x2 minors, or in German it's called Untermatrizen, are basically the matrices that you get by cancelling out a certain number of rows. Let's say you have some matrix with a number of rows and columns, and then you cancel out a lot of the rows and columns such that only a 2x2 matrix remains. The statement that the full matrix has at most rank 1 is equivalent to saying all possible 2x2 submatrices or minors have zero determinant. And the interesting thing is, if you do that, if you exploit that property of ranks of matrices in this setting, then what you can show is that if you look at these 2x2 minors here, you scratch out various rows and columns, what you find is that the constraints only depend on 3 images at a time. And so what this actually tells us is that the multiview constraint on matrices is can be reduced to constraints involving only three lines at a time or 3 images at a time. Meaning I don't actually gain more by considering 4 images simultaneously. If I take 3 images and all possible triples of images, then I have all the information I need. So this is interesting. So here you see that we can use properties of linear algebra to tell us something about how much information do we gain by considering more and more images. So considering more images is helpful, but you don't have to consider 4 images at one time. It's sufficient to always consider triples of images. Some statement about the uniqueness of the pre-image. So the idea was to construct these multiple view matrices for m observations of the line, and to use that rank constraint to assure that there is a reconstruction. We showed that the multiview constraint is equivalent to trilinear constraints, and in fact this is the set of trilinear constraints that it is equivalent to. And as I said, it's always constraints involving 3 images, I, J, K, and so for the 3 camera setting, these are the trilinear constraints. And so in the case that you observe three cameras, a line in 3D in three cameras, these are the constraints. And if they are fulfilled, then you have a unique pre-image, except for the case that in which the pre-image of every Li is the same plane in space, and that happens if the translation is inside the pre-image, right? So if I observe a plane and I move inside the pre-image span, so if I observe a line from one image, it defines a pre-image. If I move in that plane with my camera, then all observed lines are going to be the same, define the same plane. But as I said, that typically is a degenerate case. In that case, actually, the multiview matrix becomes 0 and its rank is 0. So there is a pre-image, but it's not unique. Here some examples of what can happen. Again, I mentioned these before. Once you observe three lines, just imposing that pairs of observations should be consistent is not sufficient. So only considering two images at any given time will not give me a consistent reconstruction. Because if I consider the first two images, this is a consistent reconstruction. If I consider the first and the last image, this line is a consistent reconstruction, but they're not the same line. And so here you clearly see that using more than two images helps. But you can imagine if you have three images in what's called a general configuration, and then they all intersect in that line, that's actually sufficient to specify the line. And so what you want in practice is a unique pre-image, so you want a reconstruction where the lines observed in multiple images not only intersect the various planes, but they all intersect in the same 3D line. So to summarize, if I see M vectors Li representing images of lines in M camera frames, then they correspond to the same line in 3D if that multiview matrix ML relative to any of the camera frames, if the rank is 1. If its rank is 0, if its rank is 2, there is no reconstruction. If the rank is 0, then the pre-image is determined up to that plane. And so the matrix is 0 and its rank is 0 if you move inside the pre-image of the line of the first frame. And so here is the three cases. Rank 2, no correspondence. Rank 1 means you have a unique pre-image, a unique reconstruction. And rank 0 means the pre-image is not unique. And that third example only happens if you move in the plane spanned by the first observation. To summarize the entire class or the entire chapter here on multiple view reconstruction, we showed that one can generalize the two-view scenario to multiple views, to simultaneously considering M larger or equal to 2 views, 3, 4, 5 views. And we then replaced the so-called epipolar constraint from the two-view setting by rank constraints on matrices. But what we also saw in that context is that the rank constraints are not as practically usable. They are more difficult to get into a working algorithm. For example, decoupling the structure and motion problem, like in the 8-point algorithm, was not feasible here. And the way we can summarize these relationships or these rank constraints, to have a reconstruction, we can say we constructed different matrices NP, WP, MP, and similarly you can I don't think I mentioned the matrix NL. I worked directly with WL and ML, so you have these matrices and you can impose rank constraints. And ideally you want to use the most compact representation of the rank constraint, saying some matrix has a rank at most 1 means its rows are linearly dependent, the columns are linearly dependent, and even more, if the rank is 1 means there's only one linearly independent row or column, and that means all rows or columns must be multiples of each other. And we show that these rank constraints capture the relationships among these geometric primitives in multiple images, and we showed that you can impose existence and uniqueness of the pre-image. And we remember existence is assured by having a rank less or equal to 1. Uniqueness is assured by having the rank exactly 1. If the rank is 0 of these multi-view matrices, then we have reconstructions, but not unique ones. Unique, as always, up to scaling. And we showed that in principle, this rank constraints can be used to construct a factorization algorithm for multi-view structure and motion, where we alternatingly estimate the camera motion and the 3D structure of points. In each case, we have a closed form solution using linear algebra, singular value decomposition, or least squares, a closed form solution for the structure given the motion and for the motion given the structure. But as I said, it doesn't decouple. I said here generalization of the 8-point algorithm, but it has that shortcoming that you have to alternate. So that is the last part about these linear algebra techniques. In the next chapters, I wanted to give you a little glimpse into variational techniques to do 3D reconstruction. So this is a slightly different approach, a different paradigm to do it. But this should be interesting as well for you to see what are alternative algorithms that are used nowadays to reconstruct not just points, but actually dense surfaces. Thank you.